So, concave and convex mirrors. You've got your quick and dirty mirror cheat sheet. The very first thing is the mnemonic of remembering which is concave and convex. When we're referring to the curved side, we're always talking about the mirrored side. So whether the mirrored side is inside the curve or outside the curve. And on a concave, the mirrored side is inside the cave. That's the only way I've ever figured out to remember it. So with a concave mirror, this is the mirrored side. Okay. Okay, so concave mirrors are kind of the most interesting because you can get a real or a virtual image. It depends on how far out from the mirror you put the object. And I have a set of concave mirrors for you to play with. You're looking with the bubble part away from you. Hold it straight out from your face and move it as far out as you can and then back towards your nose and watch what happens. So this gets us to the idea of upright and inverted images. So you've now seen both of them. You can, yeah, don't try not to get fingerprints on it. They're cheap, crappy little mirrors, but hey, I can find them, so that's good. The virtual and real is a little bit harder to demonstrate with this. We're going to kind of trust the math. But you see that inverted versus upright image is dependent on how far you, the object, is from the mirrored surface. So if we look at this, concave mirrors tend to focus light towards a central point. And let's draw a concave mirror. Okay, so what I've got here is a concave mirror. So the mirrored surface is towards that red dot. That red dot, and this is a little, actually wait, let me redraw that, hold on. The easiest way to construct this, the reason I'm constructing this so carefully and the reason I don't typically do this on the dosseri, I remember now. It's really difficult because you actually have to find the center point of the circle. It's really easy if you use your finger as a compass on the board to do that. It's harder on dosseri because I don't have a geometry tool on here that works well. So, that look like the center of the circle to you? My world's a little bit off today. So, well, that didn't work. That does not look centered to me. But, you know what? Maybe I can fix it like that. Does that look centered? Okay, it's probably close enough. Now what I'm going to do is I'm going to erase half my circle, a little bit more than half my circle, and then I'm going to select this whole thing and I'm going to expand it really until I lose a lot of that circle. Okay, so that's a concave mirror, and that little red dot is my center of curvature. Shrink down my text here. Okay. That center of curvature is important. Oops. Okay. So we've got these normal lines for every point, and we could draw these like, you know, a million spokes on a wheel. We typically don't, but we could. And those normal lines all converge at the center of curvature. The center of curvature is where you would stick the point of a compass down to draw the surface of this mirror. And this is actually a fairly extreme, you know, we end up drawing, because we're using primitive tools, like sort of hemispherical convex mirrors. They're usually much shallower than that in terms of the portion of an arc they use. I'm going to get rid of all my little spokes here. Whoops, that didn't do that. Okay, and I'm back to just my mirror. This is the other part that makes it a little bit tough to draw these on dosseri, and it makes it easier to actually do it on paper. There is a spot called the focal point, and for a concave mirror that exists halfway between the center of curvature and I'm going to pick another color for this. I'll do the principal axis in blue. Halfway between the center of curvature and the mirror surface. And that focal point, so I'm going to estimate it at about there. It's usually given as F. So far we've established the center of curvature, F, this blue line that I just drew in. It's an imaginary line, and there's no real line, but what we call this is the principal axis. Okay, so at this point you've got the mirrored surface, the focal point, the center of curvature, and the principal axis. That's actually everything that you're going to need to figure out where an object will appear and if an image will be real, virtual, inverted, upright, magnified, or reduced. Okay? Because we can do this two ways. We can do it This is kind of like doing vectors where you can do a graphical vector construction or you can figure out your vectors mathematically. We're going to do the same thing here. We're going to figure these out graphically and mathematically. Okay, so I have an object. This is the other reason that I typically don't do this on Doceri. I'm remembering more and more as I try this. I need a good measurement tool. So where the image is going to appear, and actually I am also going to, I'm going to move this because I'll need some space behind the mirror potentially. So I'm going to shrink that. I can get rid of a little bit of that. Okay, so we have an equation for this, which some people prefer the equation, some people prefer the graphic. I think they work nicely together. And I will be expanding this again, but for right now I just need to, oh, that's not so good. Wait a second. Let's get rid of all that. Okay. There we go. That's reasonable. Okay. Oh, for Pete's sakes. I don't know why it's doing that, but we'll just kind of ignore it. So, 1 over P plus 1 over Q equals 1 over F. It's an equation made up of reciprocals. So the reciprocal of the object distance plus the reciprocal of the image distance is equal to the reciprocal of focal length. It's easy, actually. Typically, what you're going to be given is focal length. So you're typically solving, this is the thing that you're most commonly solving for, is where is the image appearing. So if we do one of these as sort of a sample, okay, if we say that the center of curvature is 20 centimeters, what would the focal length be? 10 centimeters, because it's half. And just eyeballing this, I'm going to say that this is 15 centimeters. So the question is, where is the image going to appear? Well, we've got P, the object distance, is 15.0 centimeters, and F, the focal length, is 10.0 centimeters. My writing is terrible. We'd like to know where the image is going to appear. Now, here's the part you're going to love. You don't have to do any conversions. It does not matter what units you're in. You can be in centimeters, meters, miles, feet, cubits. I don't care what you're in. Doesn't matter. As long as all your units are the same, it all works out. So that's the first nice thing. Well, we want to solve for 1 over Q in essence. So we know that 1 over P plus 1 over Q equals 1 over F. And I should not have done that because this thing is not going to let me move that when I need to. So 1 over P plus 1 over Q equals 1 over F. Okay. 1 over Q equals 1 over F minus 1 over P. Now, at this point, you can just solve for 1 over q and then just take the reciprocal. Your other option is to, of course, say that q equals 1 over the quantity 1 over f minus 1 over p. Okay. It's not hard algebra, it's not hard math. So now let's figure out where our image is going to appear. You got a round number for q? 30 centimeters. And we get 30.0000 with a 3 finally stuck out there. So we'll call it 30. Now the question is, where is 30 centimeters on this mirror? Here are a couple other things that you should know. If a number is positive, it's in front of the mirror. If a number is negative, it's behind the mirror. Is this image in front of the mirror or behind the mirror?
In front of it.
It's in front of the mirror. And I'll get rid of my little principal axis label here, if it'll let me do that. This image is actually appearing, see if I can sort of dead reckon it, out here. So the image is actually out there. Now I drew it badly. And this is actually on your cheat sheet. Positive image distance in front of the mirror, negative image distance behind the mirror. The cool part is, if you have a positive image distance, that means rays are actually coming together in a spot in space, and if you stick a sheet of paper there, you will see an image of the object. We can't do that in here without tinfoiling all the windows and getting all the lights off, which involves removing tubes, so we can't do it. We actually did manage it in the old room. That's pretty darned easy, yes? The math is really simple. What's nice is that there's another way to come at this, which is with ray tracing. So first let's do magnification and then we'll do ray tracing. Okay, is there any possible way to, can I shrink all this? Will it let me? Okay, I can shrink all that. So magnification is how big the image looks compared to the object. If a magnification is given with a capital M, if magnification equals 1, guess what? They're the same size. So in a flat mirror on your bathroom wall this morning, that flat mirrors typically have a magnification of 1. Well, they do have a magnification of 1. You look the same size in the mirror. You're showing at real size. Magnification is equal to the height of the image divided by the height of the object. It's a ratio. That's all it is. So here's a quiz. If you have a magnification greater than 1, what does that mean about the image height compared to the object height? Image height is larger. It's enlarged. So a magnification of 2 means that the image is twice as large as the object. Magnification of 0.5 would mean what? It's half. Yeah. The image height is half the height of the object. Now, as it turns out, I didn't give you object or image height. So how would you figure out magnification? Well, there's a handy workaround. Because if you look on your cheat sheet, it's also equal to the negative of Q over P. So I'm going to shrink this. So if we take the negative, we figured out Q, and we have a Q of 30. We have a P of 15. So what's our magnification? Negative 2. And what does the negative mean? So what we know is that this is 2 times its size. So this thing, and let me see. Okay, I can get rid of that. Okay, we know it's 2 times its size, and I didn't do a good scale there. The negative actually means that it's inverted. So this object, a negative magnification means that this thing is upside down. I'm doing a very bad job drawing this. Okay, so magnification of -2. There are no units. The units cancel. It's a ratio. But a negative magnification means that it is inverted. Magnification larger than 1 means that it's enlarged. Okay. It's about enough to chew off at one time. Sorry. What I'm going to do is give you a couple of problems. If you look at number, well, I'll tell you what, on 14B, page 536, 1 through 4, get started on doing this mathematically. Tomorrow what we're going to do is learn how to do this graphically, how to do ray tracing solves, which you'll either love or hate. It's like doing, graphical vector solutions. So, I know, it was a lot. Questions, comments, etc. The basic structure we're going to do for this, we'll do concave and convex mirrors together, mathematically and graphically, and you'll have a quiz. There will be no test for this. So the quiz will be basically all workout. It'll be just like a FIP quiz, but it'll be a low point quiz. So probably about 20 points. Just doing the math for this, and the math for this is pretty simple, and doing a graphical solve. So, questions, comments, concerns?
When will that be?
Probably next Tuesday. So, we're going to spend about 2 days on concave, 2 days on convex, and then a day of sort of wrapping it all up. That's it.